Let's see, start that. All right, so thank you for having me today. Really, what I'm going to talk about mostly is this kind of autonomous microstructure characterization. And really, the way I think about this is I think about it in the context of something much bigger. And really, this is just a stepping stone. Because really, the dream of this materials design concept that is existed forever, but really been focused on more the last, say, 10, 15 years or so, is being able to actually connect individual atoms, so that purely atomistic picture, with experimental design. And we've seen talks over the last 2 days now that have mentioned this, that have talked about it in great detail to some extent. And I'm going to approach it from the purely computational perspective. Right, so I will run these atomistic simulations, and then what do I do with that information? Ultimately, I want to connect that to some sort of experiment that gets done, and how do I do that, and how do I bridge this enormous gap where the simulations that I'm running, they may not necessarily correspond perfectly with what's being shown or what's being observed at the experimental level, right? But how do I bridge those gaps? And I'm going to approach, and so that's kind of what the context of what I'll show today is approaching it from that very first step of that purely atomistic perspective, and what do I do with that information? So from a high level, I've really broken the talk into 4 pieces, right? So there's this first kind of general overview of machine learning, that kind of gives you a context for why some of the design choices that we made in this work were chosen. From a characterization perspective of these individual atomic local environments, what have people done, and why is it not necessarily sufficient for what we want to do? And then that kind of builds into this idea of characterizing microstructures. It's challenging from the atomistic perspective, and it has very different challenges than, say, the experimental perspective, where it's predominantly, say, an image recognition type problem. From the atomistic perspective, it's very different, right? The microstructures we're working with are purely 3D. We are treating each atom explicitly, and that brings its own level of challenges into it. And then kind of how are we making that next step to aid in that characterization process, using this kind of graph-based machine learning approach, rather than some of the other methods that people have chosen over the years. So I'll start off again with that general machine learning overview. So as everyone in this call is probably familiar with, we're in this kind of period of time where machine learning, data science, AI, whatever you want to call it, it's really taken off within the material science kind of domain. And now each domain has its own timeline for when it began to take off and where it's currently at. But for context, I actually started my PhD in 2015, so I kind of was right at the beginning of this major increase. And I've kind of been around for a lot of the at least more recent advances, and have been able to meet the people that actually made them, and watched them kind of happen as they as it evolved. And really, there's 3 key areas that machine learning has aided materials research. The first, which is this top picture, is really from the design perspective, right? So how do we take the information that we have and kind of design new materials, whether they be polymers or ceramics or alloys or whatever materials class you can think of. How do we take the information that we already have, condense that into something that an algorithm can actually understand, and then use that kind of learning process that machine learning is pretty good at doing to actually design new materials. And then this pipeline of, all right, well, I want to pick the materials that have the property I want, and so on. The second is that more property prediction aspect of it, right? That if I have some way of representing my material, how do I predict the properties of it, right? Because oftentimes, predicting the property that we want is either computationally, impractical for the type of material that we want to actually study, or it runs into its own series of challenges where we may not even necessarily trust the prediction that's being made for a variety of reasons. And that doesn't mean machine learning doesn't have that same problem, but there are ways of kind of ironing out why machine learning is making the prediction it is in perhaps a slightly more intuitive way. And then the third is classification, right? You have this image of some sort of disordered phase of a material on a pretty large scale compared to an atomistic simulation. You can still run an atomistic simulation on 100 nanometers, or even larger than that. But this is really the cusp of where we're talking atomistically, and in kind of picking out from the images that you get experimentally where, say, certain defects exist in the material, right? Teaching, machine learning algorithms to recognize certain things, certain patterns, and then, obviously being able to make those predictions on the fly. This, in my opinion, is predominantly where experiments or experimental integration with machine learning has been. Is really in this kind of classification regime, whereas from the atomistic perspective, you're really in the top two predominantly, right? You have a structure, what you're looking at least in principle, and how do I make a property prediction? So ultimately, the big question is, how do we bridge those two regimes, right? Is that this classification regime with a prediction regime, and then bridging those gaps between the atomistic perspective and the experimental one. Really, that can be broken down into four primary challenges that machine learning has, and I say in material science, but it really is in any domain that you're planning on using machine learning in. In my opinion, these are the four biggest challenges that you need to overcome if you want your machine learning kind of paradigm to be reliable. The first is representative data. Ultimately, you have to train your machine learning model on something, right? It's not, a purely empirical thing where you're really, tweaking your parameter set to get you 4 values and then you hope it works from there on. It's interpolative, right? So you need to have representative data. And then there's always the question, and this will go into transferability of, how does that data actually map onto, say, a much larger phase space? Is it sufficient? The second is feature representations, right? Ultimately, you're not, giving, the machine learning models just, the data itself, right? And saying, learn something from it. You're featureizing the data that you have in some representative way. And is that feature representation sufficient to learn the information that you want to learn from it? Model fitting, which is not unique to machine learning, but it still exists within the machine learning domain. Am I overfitting my model? Am I underfitting it? Is this actually sufficient for the things that I want? And then you go into model transferability, which is, now that I have my model, well, what do I do with it? Right? I mean, that's obviously the probably one of the bigger challenges that people have, which is, I've trained this model on this set, the model looks good, the features are representative, the data looks sufficient, and then I go to use it on something and then it fails, right? So then why does it fail? And the reality is that these are not individual problems, right? They're all coupled together. Each one of these feeds into the other. And so how do we actually create a way of overcoming these things? And this is kind of where I go to this physics-informed nature, right? So this is predominantly, in my opinion, why machine learning fails. If I have all of this data, and this is what my machine learning model is going to see, a number of questions arise, right? Down in the bottom, you look at this point down in the bottom right, is that really an outlier, right? Or is my data just, the data that I have is it too sparse, essentially, right? Is it not sufficient to gain the insight that I want? Are the distances between these points physically meaningful? That comes into the feature representation, right? These points actually exist in some high dimensional space that we're just showing here as 2 dimensions, but are the distances in that space meaningful? How many clusters are there really? right? If I want to make property predictions, which goes into the last tag there, I would expect similar areas in this hyperspace where points cluster together. I would expect their properties to be similar. Otherwise, making a machine learning model is going to be useless, right? If I'm feeding it all this information where the x value is essentially the same, but it has wildly different properties, machine learning is probably going to average those out and give me a prediction that is wrong for all of them. So this is why I'm a firm believer of this introduction of physics informed, right? Rather than making a purely interpolative system, add some of the physics back in, right? If this is really what the true answer is, right? Where, these kind of natural clusters form and maybe we just don't have enough data to really map this out, it turns out the answer to that outlier question is no, it's not an outlier. It actually belongs to the gray cluster. It's just we don't have enough data there. The distance in the x direction matters more than the distance in the y in this case. It turns out there are 3 clusters, and so on and so forth. So if you can add back some of the physics before you send it to the machine learning model, you're probably going to have a significantly better time with your actual predictive capability. Otherwise, you're hoping that this hyperspace that you've created with the data that you have is sufficient to just interpolate, parameterize, and hope that the model is sufficient for what you want it to do. So I think that if you can incorporate some of the physics back into it, your model will be far more impactful. So this plays into the atomic characterization perspective. So really, we've seen a lot of this over the last, say, 10 years or so, predominantly because you have the rise of things like machine learning interatomic potentials. And ultimately, other than something like DFT or embedded atoms, so it's more semi-empirical models where you just have the positions, that's not sufficient for the machine learning model, right? So you have this introduction of symmetry functions and various ways of characterizing these local atomic environments. And in many regards, they're quite good, right? If you have these various coordination shells, a lot of times these symmetry functions do a very good job of dictating and identifying where atoms exist within the local neighborhood. You have this first, second, and third coordination shell, and it correctly identifies which atoms belong in which shell, and so on and so forth. But there are drawbacks to this. So, one of the drawbacks is interpretability. If I pick a random point in this PCA space, where each point represents an atomic environment, I can't say for certain which kind of area in the phase space that point belongs in. If I pick a point that's kind of somewhere in the middle of those brown and red regimes, I can't confidently tell you if I have a surface, a grain boundary, some sort of bulk like vacancy area, right? There's no way to say for absolute certain that, yes, this is my environment. And the problem only gets worse when it turns out, and I get that this is a fairly complicated image, but the point that they're trying to make here is that on the left, you actually have structurally identical environments that have completely different feature representations, because it turns out that the directional encoding that is the reason why they're the same is not captured by the features that they're using. And similarly, on the right, you have these purple and red structures, which are structurally very different from each other. But from a feature perspective, their features are the same for a similar problem in which these things are just not unique enough to actually give you the information that you want. And then something that'll play more of a role in the talk that I'm giving now is this kind of grain boundary characterization in this case, I'm using an Ackland-Jones characterization method. The question is, where does my grain end and where does my grain boundary begin, right? In this case, green is FCC, blue is BCC, and white is, who knows. Which of these atoms belong to the grain and which of them belong to the grain boundary, right? There's no intuitive way for me to say, yes, this atom goes in this bin and this atom goes in this bin. So the takeaway here is that the uniqueness and interpretability of the methods that people have come up with are just not sufficient to do the types of problems that we're looking at, and in particular, things like microstructure characterization. You may be able to tell me, yes, this is a perfect atom and this is not a perfect atom, but really when it comes down to it, you don't know for certain where those atoms belong in terms of something higher level, like a grain versus grain boundary. So why graph neural networks? So part of the choice here is that graphs themselves tend to be a lot more intuitive rather than these, say, high-dimensional, highly parameterized functions. And part of that is because you're not approximating the physics or the geometry or the structure, right? You're explicitly capturing it with the graph, and then you're just telling the graph neural network, learn the important aspects of this graph itself. So from a characterization perspective, up in the top left, you have these different chemical reactions, and the graph neural network paradigm does a pretty good job of actually telling you which reactions are similar to one another. Down in the bottom, you have this, I believe this is a COVID-19 protein, and the idea is, if you have these beads that make up the protein, well, I need to coarse grain that in order to do a simulation. Well, how do I know which beads belong to which grain, a coarse-grained particle, right? The graph neural network does a very intuitive job of telling you which particle actually belongs to a cluster, so a much larger kind of coarse-grained bead. And then similar from a predictive standpoint, you have all these complex molecules, and traditionally these symmetry functions tend to do an okay job, but not a perfect job at capturing the properties of these molecules, in part because you have things like dihedral angles, directional encodings, things that are just not explicitly captured. So the graph neural network does a pretty good job of actually mapping to those properties. So this kind of culminates, though, in the actual microstructure perspective, right? So why is characterizing microstructure a problem? So I'm showing 4 examples here. CNA, Vorontok, this probabilistic diffusion metric that people came up with, and kind of a smoothness metric. And really the smoothness metric is actually just a normalized Steinhart order parameter. So something similar to common neighbor analysis. And the reality is that you get very different pictures of what's happening. And ultimately, none of them give you a very intuitive way of thresholding. And by thresholding, I mean, at what point do I call this atom the grain boundary, and at what point do I call this atom part of the grain? When you have binning based on just, I don't know what it is, versus I know that it's close to a reference, it becomes very difficult to actually judge where atoms belong. And that's the case for something like CNA and Vorontok. This probabilistic diffusion metric that people came up with, it has difficulty actually determining any of the properties. You can kind of see the rough outline of where the grains begin and end, but there's really no good way to actually say, yes, this atom goes here and this atom goes here. Arguably, the best one is the smoothness metric, but the smoothness metric still suffers from the same problem that these kind of bond angle order parameters suffer from, which is that as the system becomes more and more perturbed, I begin to get significant overlap between highly disordered and, a perturbed crystal structure. So there's no intuitive way to say, yes, pick 0 as my value here, and anything above it is a grain, and anything below it is a grain boundary. You're still missing that intuitive thresholding capability, and that's really what the problem is with existing methods, is that there really isn't a good way to intuitively say, yes, this atom goes here and this atom goes here. And in particular, having some way of quantifying, some level of uncertainty that when you make that decision of which atoms go where, how can I put an error bar on that, essentially? How can I say, if I do it this way versus this way, what does that do to the property of my material? So people have kind of taken a different approach with machine learning to try and do this from a microstructure perspective. So on the top, we start with the purely atomistic perspective, and then we voxelize it. And then when you voxelize it, you can threshold the voxelization, and then you can use machine learning to kind of do an image recognition between the thresholded view and the clustered view, and then kind of use another machine learning algorithm to go from the clustered view back to the atomistic view. And while this is certainly impressive, it does suffer some drawbacks, right? Anytime you voxelize something, you're reducing the accuracy. And in order to get the accuracy that you really want, you need infinite voxelization, which is just the original 3D structure. And the problem is that this requires a lot of reference information to go from the threshold to the cluster, and then from the cluster to the back map view. And what happens when you're presented with a microstructure that is very different than the one you've already seen? The second one is kind of this very interesting approach, which I'll talk about later, in which if you already know the microstructure, this provides a very intuitive way to construct a higher level graph from that microstructure and ultimately be able to map that to a given set of properties. The problem is that this method doesn't actually do the characterization, right? It assumes you already know where those grains are, what the information about them is, and so on. So while this could provide a very useful tool to do kind of this multi-scale graph approach, it still requires you to know where all the grains and everything are in the first place. So that brings us to where we're here. So this is the method that we've come up with, and hopefully it'll become clear why this approach is a little bit better, actually probably arguably a lot better than the methods that exist now. So the idea behind this is that if I take my atomistic perspective and I construct a graph out of it, I can then tell that graph information, I can tell the information within the graph, all of the information about the actual system. If I wanted to, I could encode things like bond angles and so on. In this case, for the work I'm doing here, it's not necessary. But I can encode all of the relevant structure and physics that I want at the node level in the graph, and then just teach the graph neural network how that information maps onto a local order parameter. And I think this is where this kind of physics-informed nature comes in, is I'm not approximating it with symmetry functions anymore. I'm actually learning it explicitly. So the order parameter itself is actually quite simple. It's shown up here. There's lambda I. It's really just a sigmoid function where we're ratioing the x-axis between the melting temperature of the phase of that phase with the current temperature that you're at during an MD simulation, raised to some semi-empiricism to m power, which in this case will be 3/2. What this actually does, though, is that order parameter of 1 is the perfect ideal 0 Kelvin crystal. An order parameter of 0 is a pure liquid phase at the melting temperature. And then everything in between is some mix and mash of those two based on what the graph neural network learned as you provided it these snapshots during training. So really what we're doing here is the order parameter value itself is kind of a distance in space between these two phases of the material. And in this case, everything is going to be shown for just FCC aluminum as kind of this case study. So when we actually train it on just those bulk structures at different temperatures, how does it actually perform for the types of systems we want? So this is the case of several contrived grain boundaries. So you may say to yourself, well, there isn't really much of a difference, in this kind of order-disorder metric at the interface regions. And that's kind of accurate, though, for these types of grain boundaries, because these are very contrived, highly symmetric boundaries where we've essentially just cleaved a portion of the crystal and matched them up together. So there isn't really a lot of disorder present in these systems, but the GNN plus order parameter kind of paradigm here, it still tells you where the boundary exists, and it gives you an intuitive reason for why the boundary exists, right? Instead of saying, oh, well, this atom is different than this one, we know why it's different and we know how much it's different, right? Now, what about scenarios that are very different than the training? Remember, it's only trained on bulk systems at different temperatures. Well, for the case of, say, solid-liquid interfaces, void regions, even surface regions, and these very complex polycrystalline regions with millions of atoms, it does an exceptional job of characterizing these environments, again, even though none of these are actually shown during training. And in my opinion, this is really the power of the graph representation over, say, the highly parameterized function representation, is that I don't really need to show it all that much information in order for it to really gather the underlying physics and structure and geometry that we're actually looking at. So from a more disordered perspective, how does this actually perform? So if we run these two-phase simulations at different temperatures, you can see that the perturbed crystal, at 200 Kelvin, it still recognizes it as a crystal. Even at 1,000 Kelvin, close to the melting temperature, it clearly discerns between the highly perturbed crystal structure versus the liquid structure. And then as we move into the pure liquid phase, it correctly identifies all of the atoms as being in that liquid phase, that highly disordered phase. So this gives us confidence that when we use this during, say, dynamic microstructure simulation, that it won't just immediately, you know, fall into the same trap that the other methods fall into, that it will still preserve that underlying information that we want between grain and grain boundary. So how does this actually work? The way that this works is that we do a thresholding. For the purpose of this, we're simply saying anything less than 0.5 will be the interface, and anything greater than 0.5 will preserve as the grain. Once we have that characterization at the atomic level, we can then break that system into a graph again. That graph will then be composed of subgraphs, right? Because we remove the grain boundary atoms. So all we're left with are the grain atoms, and we can do that because we've thresholded it, right? I know that I'm calling anything you know, less than 0.5 an interface atom, so I'm going to remove that. And what I'm left with is a graph of the system that contains many subgraphs. And then each one of those subgraphs is then accordingly a grain. And I can easily search for those things with just a recursive search algorithm on the graph itself and identify exactly where the grains are down to the individual atoms, and get their exact shape and size that I'm looking for. So when we actually do this during a dynamic simulation, so this will be, I think, yeah, 250 Kelvin, so it's about 60,000 atoms, but it's a 3x3x3 replica of that simulation. You'll observe that the grain nucleation occurs in stages, and each stage along the way, we're predicting that atomic order parameter at each one of the time steps. You can see initially some of those extremely small grains kind of immediately get swallowed up, and that as time goes on, those grains eventually coalesce, and we are left with just a single phase with some edge dislocations. So when we actually go to analyze this, though, using the same method that I just showed you, we can see that each one of these stages produces a very different microstructure. And we have a way of actually characterizing the shape and the size of those grains using this theta G. And you can see that at the initial time equals 0, you have a lot of very kind of small grains, which you can see up in the top right. And then at each stage along the way, the grains kind of coalesce, and you get larger grains, and you get less of them until you finally reach just before the final coalescence, where you just essentially have one tiny grain in a very large grain for all intents and purposes. So really the next stage of this, which we haven't gotten to yet, but it is the next part of this, which is kind of this mapping up to the microscale. So we have the atomistic perspective. We can confidently not only identify the grains themselves in an autonomous way, but also characterize them in a meaningful way. The next step is really to plug it into this kind of idea of, once you have the grains, you can map it to an additional graph, right? Where the information is then encoded at each one of those nodes in that higher level graph and then mapped onto a property. So you can imagine that during the MD simulation, we can identify the grains, construct a second graph from the grain picture, and say map that onto the yield strength or the bulk modulus, fracture strength, anything like that, where you can then, as you're running the simulation, see how those properties change as a function of time and temperature and any other external condition that you can think of. Because the paradigm that we're showing here is independent of external conditions, right? It's simply just looking at the individual atoms themselves. It doesn't care what pressure it is. It doesn't care what temperature it is, right? So you can confidently say that as I change those, say, pressure, temperature, whatever, that I'll be able to map it onto those properties accordingly. And the real key to this kind of workflow here is just generating enough data such that you could train that secondary machine learning model to map from that multi-level graph back to the property. So kind of to summarize, what I've shown is that we have this graph neural network scheme that actually learns the relative orderness between two phases as a local atomic order parameter, and encodes the relevant physical and geometric information of the atomic graph and maps it onto that. And that these predictions can be easily thresholded after they've been and then converted to a graph for ultimately the autonomous microstructure characterization of whatever material phase that you're interested in looking at. So I guess with that, thank the LDRD department for funding this, and take any questions that anyone has.
Thank you, Dr. Chapman, for the exciting talk. This is a really exciting topic. I believe there are lots of questions. So yeah, please, if you have questions, please go ahead.
Can I ask a question?
Of course.
Hi. Hi, Jim. That's very nice talk. I really enjoyed that. Can you hear me?
Yeah.
Yeah.
Oh, yeah. So I have a question. So in your graph neural network, how many elements you can deal with? Or is there any limit on that?
So that's a good question. So from what we have so far, just one. This is really the proof of concept of, how do we, I mean, the order parameter itself is unique, right? It's a slightly different approach as opposed to, say, the bond angle approach people have traditionally taken. And in principle, from a simulation perspective, a theoretical perspective, there is no limit, right? Because as long as you can construct an atomic graph that appropriately encodes the information, the GNN most likely will be able to learn it. Now, granted, as you introduce more elements into the system, you're introducing more complexity in terms of configurational space, right? There's more possible combinations of where everything can go. So you'd probably need more data to appropriately train it. But there is no theoretical limit to how many elements you could have, as long as you could construct a physically meaningful graph from that system.
I see. Yeah, thank you.
I have a follow-up question on this. Say, I believe in this graph neural network, each atoms are connected. So say how many layers of neural network, and then when they communicate to each other, how many iterations to make it better, outperform the traditional feature engineering method.
So this is the setup that we're using, and really there's not really a lot of complexity in the model itself, right? So this is actually one of the benefits of using the graph-based approach, as opposed to some of these more kind of brute force, highly interpolative, high-dimensional neural networks, where you have hundreds of layers, thousands of neurons, in order to really map that out. But then in reality, you're probably overfitting the model. The reality is the graph neural network approach is quite simple in comparison. And that is one of the benefits of doing it, right? Is that you're not really that far separated from that initial encoding back to the output of the model itself. Now, obviously, this would probably get slightly more complex as you introduce more elements into the system, but it would still be significantly reduced, both computationally and complexity-wise, from some of these other systems. When you think about some of these highly parameterized symmetry functions, which could potentially have hundreds of dimensions in them, and then now you then have to still feed that into, say, a neural network model or another type of regression model in order to make a prediction. You're introducing a lot of complexity that ultimately loses some of that important information. Whereas here, because of the simplicity of the architecture itself, you're preserving a lot of that, the initial physics that you've given it, in a much simpler and intuitive way.
Wow, this is surprising. So you believe this graph neural network approach is computationally more efficient than the old feature engineering, the order parameter method?
Well, I think that computationally efficient, when we make the term in terms of, say, predictive capability, right? So how long does it take me to hit execute and give me an answer? Obviously there's a lot that depends on that. Maybe you found a way to make a reduced high dimensional neural network that somehow based on the parallelization you do outperforms the simple graph neural network. But the reality is that from a intuitive perspective, the time it actually takes to design the features, the time it takes to know that your model isn't overfit, to know that your model can extrapolate reasonably, the complexity is certainly reduced when it comes to the graph-based approach, right? Because I'm not telling it what the features are, right? I'm simply constructing a graph and saying, learn the relevant information for me.
Yeah. From this perspective, the graph neural network approach is definitely a beautiful approach to handle this problem. Yep. Let's thank our speaker, Dr. Chapman, again for this wonderful talk.